What if I told you that a single ingredient, something that costs less than $1 a day and can be added to a cup of coffee you are probably already drinking every morning, has the potential to influence three of the most important biological systems that determine how well your body ages after 60? Not just one system, three at the same time. It may help restore the energy production capacity inside your cells. It may help protect and maintain the stem cells your body relies on to repair tissues throughout your organs. And it may help shift your metabolism away from the glucose-dependent environment that many researchers now believe supports the growth of cancer cells. For most people over 60, these three things sound unrelated. Energy decline feels like one problem, weight gain feels like another, and cancer risk seems like something entirely different. But modern metabolic research is revealing that these problems are not separate at all. In fact, they are deeply connected at the level of cellular metabolism. The surprising part is that the intervention influencing all three systems is not a pharmaceutical drug, not an expensive medical therapy, and not a complicated lifestyle overhaul. It is a specific type of dietary fat that interacts with your metabolism in a very unusual way. My name is Dr. Becker. For more than 2 decades, I have studied the intersection of metabolic medicine, cellular aging, and cancer biology, focusing specifically on what happens inside the bodies of patients after the age of 50. Over those years, I began to notice a pattern that kept appearing across different areas of research. Whether scientists were studying mitochondrial decline, stem cell biology, or metabolic disease, the same biochemical pathways appeared again and again. And eventually, those pathways led researchers to an unexpected molecule produced by the body when it metabolizes a certain type of fat. That molecule is called beta-hydroxybutyrate, often abbreviated as BHB, and understanding what it does inside your cells changes the way we think about something as simple as your morning coffee. In the next few minutes, I'm going to show you what happens inside the body after 60 that makes these systems begin to fail, why those failures reinforce each other in a downward biological spiral, and how a small metabolic intervention, one that researchers have been studying for years in peer-reviewed journals, may help interrupt that cycle. After the age of 60, the changes that begin to take place inside the body are not simply cosmetic signs of aging. They are the result of deeper biological shifts that affect how every cell in your body produces energy, repairs damage, and regulates metabolism. What most people experience as fatigue, slower recovery, increased abdominal fat, and declining resilience is actually the visible surface of processes occurring at the microscopic level inside tissues. One of the most important of these changes is a gradual loss of metabolic flexibility. When you are younger, your body can easily switch between different fuel sources depending on what is available. Sometimes your cells burn glucose, sometimes they burn fat, and sometimes they rely on molecules called ketones that are produced when fat is metabolized in the liver. This flexibility allows the body to maintain stable energy levels even when food intake fluctuates. As people age, that flexibility begins to disappear. The body becomes increasingly dependent on glucose as its primary fuel source. Part of this shift is driven by insulin resistance, a condition that develops slowly over decades. Cells become less responsive to insulin signals, meaning glucose remains in the bloodstream longer, and metabolic regulation becomes less efficient. The pancreas compensates by producing more insulin, and this elevated insulin environment encourages the body to store more fat, particularly around the abdominal organs. At the same time, low-grade inflammation begins to rise throughout the body. Researchers often refer to this process as inflammaging. Unlike the acute inflammation that occurs during infection or injury, this form of inflammation is subtle and persistent. Over time, it interferes with cellular signaling pathways, damages proteins and DNA, and further disrupts the metabolic systems responsible for maintaining health. Hormonal shifts also contribute to these changes. Levels of growth hormone, testosterone, and other anabolic signals decline with age, reducing the body's ability to build and maintain muscle tissue. Because muscle is one of the most metabolically active tissues in the body, the loss of muscle mass further slows metabolic rate. As metabolism slows, fat accumulation becomes easier and energy production becomes less efficient. The combined effect of these changes creates a metabolic environment that is very different from the one that existed when the body was younger. Energy production declines, fat storage increases, and the body's ability to repair cellular damage gradually weakens. What makes this particularly important is that these changes do not occur independently. They interact with each other in ways that accelerate the aging process. To understand how that interaction works, we need to look more closely at one of the most critical structures inside your cells, the tiny energy generators known as mitochondria. These structures play a central role in determining how much energy your body can produce, and their decline is one of the most significant biological shifts that occurs as we age. Inside every cell in your body, there are tiny structures that function like microscopic power plants. These structures are called mitochondria, and their job is to convert the nutrients you consume into usable cellular energy. Nearly every movement you make, every heartbeat, every thought, and every repair process in your tissues depends on the energy produced by these small organelles. The form of energy mitochondria produce is a molecule called ATP, short for adenosine triphosphate. ATP is essentially the fuel currency of life. Whenever a cell needs to contract, divide, repair damage, or synthesize proteins, it spends ATP to perform that work. The more mitochondria a cell contains, the more energy it can generate, and the more efficiently it can maintain healthy function. When people are young, mitochondrial networks are dense, dynamic, and highly efficient. A single muscle cell in a healthy 20-year-old may contain thousands of mitochondria operating at high capacity. These mitochondria continuously replicate, repair themselves, and adapt to the body's energy demands. Exercise, nutrient availability, and hormonal signals all stimulate the production of new mitochondria in a process known as mitochondrial biogenesis. But as the body ages, this system begins to break down. Research examining muscle biopsies from older adults has consistently shown that mitochondrial density declines significantly over time. By the time many individuals reach their mid-60s, mitochondrial capacity in muscle tissue may be reduced by as much as 40 to 50% compared with younger adults. Fewer mitochondria means less energy production, and the energy deficit affects nearly every biological system. The problem is not only that the number of mitochondria decreases, the mitochondria that remain also become less efficient. Over decades of metabolic activity, mitochondria accumulate damage from reactive oxygen species, often abbreviated as ROS. These are chemically reactive molecules produced as a natural byproduct of cellular respiration. In small amounts, they play useful signaling roles, but when mitochondrial function begins to decline, ROS production increases and can damage proteins, membranes, and mitochondrial DNA. Damaged mitochondria produce less ATP while generating more oxidative stress, creating a cycle that further accelerates cellular aging. Tissues that require large amounts of energy, such as muscles, the brain, and the heart, are especially sensitive to this decline. People begin to notice that activities which once felt effortless now feel exhausting. Recovery from exercise slows. Physical endurance decreases. Even mental clarity can suffer because neurons depend heavily on mitochondrial energy production. This gradual collapse in mitochondrial performance is one of the central biological drivers of aging. But mitochondria do not operate in isolation. Their decline has direct consequences for another critical system responsible for maintaining the health of tissues throughout the body's stem cell population. Throughout your life, your body relies on a remarkable repair system that operates quietly in the background. Every day, tissues are damaged by normal wear and tear. Muscle fibers experience microscopic injuries during movement. Cells lining the gut are constantly replaced. Blood vessels endure mechanical stress from circulation, and even the skin renews itself through continuous cycles of cell turnover. The reason these systems continue to function for decades is because of a special group of cells known as stem cells. Stem cells are unique because they possess two extraordinary abilities. First, they can divide and produce copies of themselves, maintaining a reserve population that persists throughout life. Second, they can differentiate into specialized cells that replace damaged tissue. When an injury occurs, chemical signals guide stem cells toward the affected area where they transform into the cell types needed for repair. In this way, stem cells function as the body's internal maintenance crew. Different tissues rely on different stem cell populations. Hematopoietic stem cells located in the bone marrow generate the billions of blood cells that circulate through your body each day. Mesenchymal stem cells help maintain connective tissues, cartilage, and bone. Other stem cells reside in organs such as the liver, intestine, and skin, constantly renewing the cells that allow those organs to function properly. As long as these regenerative systems remain healthy, the body can repair damage faster than it accumulates. However, the number and vitality of stem cells gradually decline with age. Studies examining circulating stem cell populations in older adults show that by the mid-60s, the available pool of certain regenerative stem cells may be reduced by more than half compared with younger individuals. Even the stem cells that remain often show signs of functional decline. They divide less efficiently, respond more slowly to injury signals, and become more vulnerable to environmental stress. Several factors contribute to this exhaustion. Over time, stem cells accumulate DNA damage caused by oxidative stress and environmental exposures. Chronic inflammation, which increases with age, interferes with the molecular signals that normally regulate stem cell activity. At the same time, the aging of mitochondria within these cells reduces the energy available for cell division and tissue regeneration. As the stem cell pool shrinks, tissues lose some of their ability to repair themselves. Small injuries take longer to heal. Structural proteins in muscles and connective tissues are replaced more slowly. Damage that once would have been repaired quickly can persist long enough to trigger chronic inflammation or cellular malfunction. In some cases, when healthy cells are not replaced efficiently, damaged cells may accumulate mutations that increase the risk of disease. Understanding this decline in stem cell function is critical because it reveals that aging is not simply the result of time passing. It is the consequence of specific biological systems gradually losing their ability to maintain the body's internal repair processes. And when this loss of regenerative capacity occurs alongside the metabolic shifts we discussed earlier, it creates an environment where another important change begins to take place. The body becomes increasingly dependent on glucose as its primary source of energy. As these biological systems begin to weaken, another important shift quietly develops inside the body, one that many people never realize is happening. The body gradually loses its ability to switch efficiently between different fuel sources. Scientists refer to this ability as metabolic flexibility, and it is one of the defining characteristics of a healthy metabolism. When you are young and metabolically healthy, your cells can easily move between burning glucose, burning stored fat, and using molecules called ketones that are produced when fat is metabolized in the liver. This flexibility allows your body to maintain stable energy levels whether you have recently eaten a meal or gone several hours without food. But as people age, this flexibility often begins to disappear. The body becomes increasingly dependent on glucose as its primary fuel source. One of the main reasons for this change is the gradual development of insulin resistance. Over decades of exposure to frequent meals, refined carbohydrates, and chronic metabolic stress, cells begin responding less efficiently to insulin. When insulin signaling weakens, glucose remains in the bloodstream longer, and the body compensates by producing even more insulin to force glucose into cells. This elevated insulin environment has several consequences. It promotes fat storage, particularly in the abdominal cavity around organs such as the liver and pancreas. It also suppresses the metabolic pathways that allow the body to burn fat efficiently. As a result, many people enter a state where they are storing fat but cannot easily access it for energy. At the same time, the body's ability to produce and utilize ketones becomes diminished. Ketones are normally generated during periods of fasting or when fat metabolism increases. They serve as an alternative fuel source that can power the brain, muscles, and other tissues with remarkable efficiency. But when metabolism becomes locked into a glucose-dependent state, ketone production decreases and the body becomes less capable of using fat as a primary energy source. This metabolic shift has implications that extend far beyond weight gain. Elevated glucose and insulin levels influence inflammatory pathways, accelerate oxidative stress, and create biochemical conditions that can affect cellular growth signals throughout the body. Over long periods of time, this environment contributes to many of the chronic diseases associated with aging. What makes this particularly important is that these metabolic changes do not occur independently of the other systems we have discussed. The decline of mitochondria, the exhaustion of stem cells, and the growing dependence on glucose are all interconnected parts of the same biological pattern. Understanding how these systems interact reveals why aging often accelerates after the age of 60. What makes these changes especially important is that they do not occur as isolated problems inside the body. They form a biological feedback loop in which each system influences the others, gradually amplifying the overall decline in cellular function. Researchers studying aging metabolism often describe this process as a reinforcing cycle rather than a series of independent failures. When mitochondrial efficiency begins to decline, cells produce less energy and generate greater amounts of reactive oxygen species. These reactive molecules can damage proteins, lipids, and even DNA inside the cell. Over time, this oxidative stress begins to affect nearby stem cells, reducing their ability to divide and repair tissues effectively. When stem cells lose their regenerative capacity, damaged cells are replaced more slowly, and the quality of tissue maintenance begins to deteriorate. At the same time, the metabolic shift toward chronic glucose dependence contributes to a hormonal and inflammatory environment that further accelerates this process. Elevated insulin levels encourage fat accumulation and suppress the metabolic pathways involved in fat oxidation. This not only reinforces the body's dependence on glucose, but also promotes the development of visceral fat, which is known to release inflammatory signaling molecules into the bloodstream. Inflammation, oxidative stress, and declining cellular energy then feed back into mitochondrial dysfunction, weakening the very systems responsible for maintaining cellular health. As this cycle continues over the years, the body gradually loses efficiency in energy production, tissue repair, and metabolic regulation. Understanding this interconnected pattern is essential because it reveals something important about aging. These systems share common biochemical pathways. That means an intervention capable of influencing those pathways may have effects that extend across multiple biological systems at once. And this is exactly where researchers began to notice the unusual metabolic effects of a specific type of dietary fat. The scientific interest in medium-chain triglycerides did not begin in the world of longevity or metabolic optimization. In fact, the earliest research on these unusual fats emerged from clinical medicine several decades ago, when physicians were searching for ways to nourish patients whose digestive systems could not properly absorb conventional dietary fats. Most fats in the human diet are classified as long-chain triglycerides. These molecules contain long carbon chains that must pass through a complex digestive pathway before the body can use them. They are broken down in the intestine, packaged into lipoprotein particles, transported through the lymphatic system, and eventually released into the bloodstream, where they can either be burned for energy or stored in fat tissue. This process is relatively slow and metabolically inefficient. Medium-chain triglycerides, however, behave very differently. Their shorter carbon chain structure allows them to bypass much of the normal digestive pathway. Instead of entering the lymphatic system, they are absorbed directly into the portal vein and transported immediately to the liver. Once there, the liver rapidly converts them into molecules known as ketone bodies, a process that can occur within minutes of ingestion. This unusual metabolic behavior first attracted attention in the treatment of certain neurological disorders. Researchers studying epilepsy discovered that diets capable of elevating ketone levels in the blood could dramatically reduce seizure frequency in some patients. The ketogenic diet became an established therapy for drug-resistant epilepsy, and scientists began exploring ways to elevate ketones without requiring extremely restrictive diets. Medium-chain triglycerides proved to be one of the most effective tools for accomplishing this. Because they are rapidly converted into ketones, even modest amounts can raise circulating ketone levels without prolonged fasting or severe carbohydrate restriction. As research expanded, scientists began noticing that these ketone molecules were not simply alternative fuels. They also functioned as powerful signaling compounds that influence metabolism, inflammation, and cellular energy systems. That discovery opened an entirely new field of investigation. Researchers studying aging biology, metabolic disease, and even cancer metabolism began asking whether these ketone signals might influence the very cellular pathways that decline as the body grows older. And the molecule at the center of that research turned out to be one of the primary ketones produced when medium-chain fats are metabolized in the liver, beta-hydroxybutyrate. When medium-chain fats are rapidly metabolized in the liver, the body produces a group of molecules known as ketone bodies. These molecules serve as an alternative fuel system that humans have relied on throughout evolutionary history during periods when food was scarce. Long before modern diets existed, the human body developed the ability to shift from burning glucose to burning fat-derived ketones whenever carbohydrate availability dropped. There are three primary ketone bodies produced by the liver. The first is acetoacetate, which is generated during the initial breakdown of fatty acids. The second is acetone, a minor byproduct that is eventually exhaled through the breath. The third, and by far the most biologically important, is beta-hydroxybutyrate, often abbreviated as BHB. Although technically classified as a ketone-related molecule rather than a true ketone, BHB is the form that circulates in the bloodstream at the highest concentrations and delivers most of the metabolic effects associated with ketosis. For many years, scientists believed that ketones were simply backup fuels used by the body when glucose was unavailable. We now know that this interpretation was incomplete. In addition to providing energy, ketones act as signaling molecules that influence how cells regulate metabolism, inflammation, and gene expression. In other words, ketones do not merely replace glucose as a fuel source, they actively communicate with cellular pathways that determine how cells behave. One of the most remarkable features of beta-hydroxybutyrate is its efficiency as an energy substrate. When tissues such as the brain, heart, or skeletal muscle use BHB as fuel, mitochondria are able to produce energy with less oxidative stress compared with glucose metabolism. This means that cells can generate ATP while producing fewer reactive oxygen species, reducing the cellular damage associated with aging. Beyond energy production, BHB also influences several regulatory enzymes involved in gene expression. One of these enzyme families is known as histone deacetylases, or HDACs. By inhibiting certain HDAC enzymes, beta-hydroxybutyrate can alter the way specific genes are expressed, particularly genes related to cellular stress resistance, inflammation control, and metabolic regulation. These discoveries have changed the scientific view of ketosis. Rather than being simply a survival mechanism during starvation, ketosis appears to activate a complex network of protective biological pathways. Researchers studying aging and metabolic disease are now exploring how mild elevations in circulating ketones may help stabilize mitochondrial function, regulate inflammation, and support cellular repair systems throughout the body. And this is where medium-chain fats become particularly interesting, because they offer a way to elevate beta-hydroxybutyrate levels quickly and reliably without requiring prolonged fasting or extreme dietary changes. One of the first effects researchers noticed when studying medium-chain triglycerides was their unusual impact on how the body burns fat. Unlike most dietary fats, which are easily stored if energy demand is low, medium-chain fats are rapidly transported to the liver and converted into ketones. This rapid conversion changes the metabolic environment in a way that encourages cells to use fat as fuel rather than store it. In clinical studies comparing different types of dietary fat, researchers observed that individuals consuming moderate amounts of MCT oil showed a measurable increase in fat oxidation. Fat oxidation simply means the rate at which the body burns fat for energy. In controlled experiments using metabolic chambers and indirect calorimetry, participants consuming MCTs demonstrated significantly higher fat-burning rates compared with those consuming the same calories from long-chain fats such as olive oil. What made these findings particularly interesting was not just the amount of weight lost, but the type of fat that was reduced. Visceral fat, the fat that accumulates around internal organs such as the liver, pancreas, and intestines, is metabolically very active and strongly associated with inflammation, insulin resistance, and cardiovascular risk. In several controlled trials, reductions in visceral fat were greater in participants consuming MCTs compared with those consuming other dietary fats. The mechanism behind this effect appears to involve ketone signaling. When beta-hydroxybutyrate levels rise in the bloodstream, it activates metabolic pathways that encourage cells to rely more heavily on fat for energy. This shift toward fat oxidation increases the demand for fatty acids as fuel. Instead of circulating in the bloodstream and eventually returning to storage in adipose tissue, those fatty acids are pulled into mitochondria where they are converted into ATP. Over time, this metabolic shift can gradually reduce the accumulation of visceral fat while improving the body's ability to access stored energy. While the effect is not dramatic overnight, consistent elevation of ketone signaling appears to push metabolism in a direction that favors fat utilization rather than fat storage. Another mechanism that has attracted significant scientific interest is the effect ketones appear to have on the creation of new mitochondria inside cells. As we discussed earlier, one of the central biological features of aging is the gradual decline in mitochondrial density and efficiency. When fewer mitochondria are available to produce ATP, tissues begin to experience an energy deficit that affects everything from muscle endurance to cognitive performance. Research over the past decade has shown that certain metabolic signals can stimulate a process known as mitochondrial biogenesis, the creation of new mitochondria within cells. One of the key regulators of this process is a protein called PGC1 alpha. This protein acts as a master switch that activates a network of genes responsible for building and maintaining mitochondrial structures. When PGC1 alpha is activated, cells begin producing new mitochondrial components and assembling additional energy-producing units. In effect, the cell expands its internal energy infrastructure. Exercise is one of the most well-known activators of this pathway, which is one reason regular physical activity is strongly associated with improved metabolic health. Interestingly, emerging research suggests that elevated ketone levels may also influence this pathway. Beta-hydroxybutyrate appears to interact with signaling systems that regulate mitochondrial function and energy metabolism. In laboratory studies, the presence of ketones has been associated with increased expression of genes involved in mitochondrial maintenance and repair. For aging tissues, this effect could be particularly meaningful. If metabolic signals encourage the body to produce additional mitochondria, even modest increases in mitochondrial density can improve the efficiency of cellular energy production. More energy available at the cellular level means tissues are better equipped to maintain function, repair damage, and respond to physical demand. While research in humans is still evolving, the possibility that ketone signaling may support mitochondrial renewal has become one of the most intriguing areas of investigation in metabolic aging science. A third mechanism that has recently drawn increasing attention from researchers involves the relationship between ketone signaling and stem cell biology. As we discussed earlier, one of the major challenges of aging is the gradual exhaustion of the body's regenerative systems. Stem cells that once maintained tissues efficiently begin to lose their ability to remain stable, divide properly, and respond to injury signals. One reason this happens is that stem cells must carefully balance two opposing states. They must remain in a protected resting condition, known as quiescence, where they preserve their long-term regenerative capacity, but they must also be able to activate quickly when tissues require repair. If stem cells leave this protected state too frequently, they divide repeatedly and eventually become depleted. Over time, the regenerative pool shrinks. Recent research has suggested that beta-hydroxybutyrate may play a role in maintaining this delicate balance. BHB appears to influence enzymes involved in epigenetic regulation, particularly a class of enzymes called histone deacetylases, or HDACs. These enzymes help control how tightly DNA is packaged inside the nucleus and therefore influence which genes are active or inactive in a given cell. When BHB inhibits certain HDAC enzymes, it can shift gene expression toward pathways associated with cellular stress resistance and metabolic stability. In stem cells, these signals may help maintain the protective quiescent state that allows the cells to remain viable for long periods without exhausting their regenerative potential. Researchers studying hematopoietic stem cells, the cells responsible for producing blood cells throughout life, have observed that metabolic signals influence whether these cells remain dormant or become activated. Elevated ketone availability appears to support the metabolic environment associated with stem cell preservation. Although the field is still evolving, this line of research has generated significant excitement because it suggests that metabolic states, including those influenced by ketone production, may directly affect how well the body maintains its regenerative capacity during aging. A fourth mechanism that researchers have begun exploring involves the unique metabolic behavior of cancer cells. Nearly a century ago, the German biochemist Otto Warburg made an observation that would later become one of the foundational discoveries in cancer metabolism. He found that many cancer cells consume glucose at extraordinarily high rates compared with normal cells, even when oxygen is readily available. Instead of using their mitochondria efficiently to generate energy, these cells rely heavily on a process known as aerobic glycolysis. This phenomenon, now widely referred to as the Warburg effect, means that cancer cells are metabolically different from most healthy cells. While normal tissues are capable of switching between glucose, fat, and ketones depending on what fuel is available, many cancer cells appear far less flexible. Their metabolism is strongly oriented toward glucose consumption and rapid fermentation of that glucose into lactate. Because of this dependency, researchers have begun investigating whether altering the body's metabolic environment might influence the conditions in which cancer cells grow. When glucose availability decreases and ketone availability increases, healthy cells with functional mitochondria can adapt and continue producing energy efficiently. They simply shift toward using ketones and fatty acids as fuel. Cancer cells, however, often struggle to make this metabolic transition. Their mitochondria tend to function less efficiently, and their reliance on glucose metabolism means that they are less capable of using ketones as a primary energy source. This difference has led scientists to explore metabolic strategies that modify fuel availability in the body. Some experimental studies, particularly in animal models, have shown that environments characterized by lower glucose levels and elevated ketones may slow the growth of certain tumors. These findings have contributed to a growing area of research sometimes referred to as metabolic therapy. It is important to emphasize that this research does not suggest that dietary strategies alone can cure cancer. Cancer is a complex disease influenced by genetics, immune responses, and many environmental factors. However, understanding the metabolic differences between healthy cells and cancer cells has opened new scientific discussions about how metabolic signals may influence disease progression. By shifting metabolism toward ketone utilization, the body may create conditions that are more supportive of healthy cellular function, while being less favorable for cells that depend heavily on glucose-driven growth pathways. The fifth mechanism becomes particularly interesting when this metabolic process is combined with something millions of people already consume every morning: coffee. Caffeine, the primary active compound in coffee, has long been studied for its effects on metabolism and energy regulation. One of its well-established actions is the stimulation of a process called lipolysis, the breakdown of stored fat inside adipose tissue. When caffeine enters the bloodstream, it inhibits an enzyme known as phosphodiesterase. This inhibition increases the levels of a signaling molecule called cyclic AMP inside fat cells. Elevated cyclic AMP activates hormone-sensitive lipase, an enzyme responsible for releasing fatty acids from stored fat. In simple terms, caffeine signals fat cells to open their storage reserves and release fatty acids into the bloodstream where they can be used as fuel. However, releasing fat into circulation does not automatically mean the body will burn it. If the metabolic demand for energy is low, those fatty acids may simply be reabsorbed by fat tissue and stored again. This is where the interaction with medium-chain fats becomes particularly significant. When MCT oil is consumed, the liver rapidly converts those fats into ketones, increasing the body's demand for energy substrates that mitochondria can oxidize. The presence of ketones signals tissues throughout the body to begin using fatty acids and ketone bodies as primary fuels. In effect, caffeine mobilizes stored fat, while ketone production encourages cells to burn that fuel. The combination creates a metabolic environment in which fat release and fat utilization occur simultaneously. Researchers studying metabolic responses have observed that caffeine can increase fat oxidation on its own, while MCT-derived ketone production also independently promotes fat utilization. When these two signals occur together, the metabolic pathways they activate appear to complement one another. This synergy helps explain why the simple combination of coffee and medium-chain fats has become a topic of interest in metabolic research. At this point, the most important question is not whether the mechanisms are biologically plausible, but whether they have been observed in real human studies under controlled conditions. And this is where the discussion becomes more grounded, because medium-chain triglycerides are not just theoretical compounds studied in petri dishes. They have been examined in a range of clinical settings, including weight management, metabolic health, neurological therapy, and age-related body composition changes. In controlled dietary studies comparing MCT oil with longer-chain fats, participants consuming moderate daily amounts of MCTs consistently showed greater increases in energy expenditure and fat oxidation. Several of these studies also reported greater reductions in body weight and abdominal fat, even when total calorie intake was matched between groups. What makes these findings especially important is that the advantage was not simply due to eating less. It reflected a measurable shift in the way the body handled fuel. Other clinical investigations have focused on older adults experiencing sarcopenia, the age-related loss of muscle mass and strength. In these studies, participants receiving MCT supplementation alongside modest lifestyle interventions showed improvements not only in fat loss but also in the preservation of lean tissue. This matters because many weight loss strategies in older adults reduce both fat and muscle at the same time, which can worsen frailty rather than improve health. Researchers have also measured changes in metabolic markers such as fasting triglycerides, insulin sensitivity, and energy utilization. While results vary between studies, the general pattern suggests that MCT supplementation can improve aspects of metabolic efficiency, particularly when used consistently and in combination with supportive behaviors such as resistance exercise and controlled calorie intake. It is important to remain scientifically honest here. The clinical evidence is promising, but it is not unlimited. Not every study is large, not every outcome is dramatic, and not every biological effect observed in the laboratory has been fully confirmed in large human trials. But taken together, the evidence suggests that MCT-derived ketone production is not merely a theoretical idea. It produces measurable metabolic changes in humans, and those changes are especially relevant to the problems that tend to accelerate with age. The question then is how to use this information correctly in real life, because with metabolic interventions, the protocol matters just as much as the ingredient itself. But knowing the science is only part of the equation. Because when it comes to metabolic interventions, the outcome is not determined by what you take, but by how you take it. The difference between a protocol that works and one that fails often comes down to details that seem small but have significant biological consequences. The first variable that matters is the type of medium-chain fat being used. Not all MCT oils are metabolically equivalent. Medium-chain triglycerides are composed of fatty acids of different lengths, typically referred to as C6, C8, C10, and C12, based on the number of carbon atoms in their structure. Of these, C8, known as caprylic acid, is the most rapidly converted into ketones. It reaches the liver quickly and produces beta-hydroxybutyrate more efficiently than the longer chain fractions. C10, or capric acid, is slightly slower but still effective. C12, often found in coconut oil, behaves more like a long-chain fat and does not generate ketones at the same rate. This distinction matters because the metabolic effects we've been discussing are closely tied to how quickly and consistently ketone levels rise in the bloodstream. The second variable is dosage, and this is where many people make mistakes. Medium-chain fats are processed directly by the liver, and introducing too much too quickly can overwhelm the digestive system. The most effective approach is to begin with a small amount, typically about 1 teaspoon, and allow the body several days to adapt. As tolerance improves, the dose can gradually be increased to 1 tablespoon and eventually up to 2 tablespoons per day if well tolerated. This gradual progression allows the metabolic pathways involved in fat oxidation and ketone production to adjust without causing unnecessary discomfort. Preparation is another detail that is often overlooked but has a meaningful impact on absorption. Simply pouring oil into coffee and stirring it leaves the fat separated from the liquid. When consumed this way, the body receives uneven amounts of fat, and the digestive response can be inconsistent. Blending the oil into the coffee creates a stable emulsion, breaking the fat into microscopic droplets that are more evenly distributed. This improves both the texture and the efficiency of absorption, allowing the metabolic effects to occur more consistently. Timing may be the most important variable of all. Consuming this combination in the morning before eating anything else places the body in a unique metabolic state. After an overnight fast, insulin levels are relatively low, and the body is already beginning to shift toward fat utilization. Introducing medium-chain fats at this moment amplifies that shift, increasing ketone production at a time when cells are most receptive to alternative fuel sources. Delaying the first meal for several hours after consumption extends this metabolic window, allowing the body to remain in a state that favors fat oxidation and ketone utilization. When these elements are combined correctly, the protocol becomes more than just adding an ingredient to coffee. It becomes a structured metabolic signal that influences how the body produces energy, utilizes fuel, and regulates key biological pathways associated with aging. When people begin any metabolic intervention, one of the biggest reasons they stop too early is because they expect results to appear immediately. But the biological systems we've been discussing do not change overnight. They adapt in phases, and understanding that timeline is what allows someone to stay consistent long enough to see meaningful results. In the first 1 to 2 weeks, the most noticeable changes are usually not physical, but neurological. As ketone levels begin to rise, the brain starts using beta-hydroxybutyrate as a supplemental fuel source. Many people report a subtle but noticeable increase in mental clarity during the morning hours, along with a reduction in the mid-morning energy crash that often follows a carbohydrate-based breakfast. Appetite may also decrease, not because of willpower, but because ketones influence hunger-regulating hormones and provide a more stable energy supply. Between weeks 3 and 8, changes in body composition typically begin to emerge. As the body becomes more efficient at oxidizing fat, stored energy, particularly visceral fat, begins to be used more consistently. This process is gradual but measurable. Clothing may fit differently before the scale shows dramatic changes, because reductions in abdominal fat often occur before total body weight shifts significantly. By the second and third months, deeper metabolic adaptations start to become more apparent. Mitochondrial function improves as cells adjust to a more consistent supply of alternative fuel. Biomarkers such as triglycerides, fasting insulin, and markers of metabolic efficiency may begin to move in a favorable direction. For some individuals, this phase is also where improvements in physical endurance and recovery become more noticeable. The key point is that each of these stages builds on the previous one. Early changes create the conditions for later adaptations. When people understand that progression, they are far more likely to stay consistent long enough to experience the full effect of the protocol. Over the years, I have had the opportunity to observe how these metabolic changes play out in real people, not just in controlled studies or laboratory models. What stands out is not a single dramatic transformation, but a consistent pattern of small changes that accumulate over time and begin to alter how individuals experience their daily lives. Many of the patients I have worked with came in with a similar set of concerns. They described a level of fatigue that felt out of proportion to their activity. Tasks that once felt routine required more effort. Recovery after exercise or even after a poor night of sleep seemed to take longer than it used to. Some had noticed gradual increases in abdominal fat despite not making significant changes to their diet. Others described a kind of mental fog that was difficult to define but easy to recognize. When metabolic interventions that supported ketone production were introduced in a structured and consistent way, the first changes people reported were often related to energy. Not a sudden surge, but a steadier, more reliable level of alertness in the morning hours. The kind of energy that did not depend on constant food intake or caffeine throughout the day. Over time, these early changes were often followed by shifts in body composition. Waist measurements began to decrease gradually, sometimes before overall weight changed significantly. In individuals who combined these interventions with resistance training, strength was often maintained or improved even while fat mass declined. which is not the typical pattern seen with standard calorie restriction. Perhaps the most interesting observations were not physical at all but perceptual. People would describe feeling more like themselves again. Not younger, in an unrealistic sense, but closer to the level of energy and clarity they remembered from earlier decades. These changes were not identical for everyone, and they did not occur at the same speed, but the underlying pattern was consistent enough to suggest that the metabolic pathways we've been discussing are not just theoretical constructs. They are systems that can influence how people actually feel and function over time. One of the reasons many people try this approach and conclude that it does not work is not because the underlying biology is ineffective, but because small mistakes in execution prevent the metabolic signals from occurring as intended. These mistakes are common, and understanding them can make the difference between seeing results and abandoning the protocol too early. The first mistake is using the wrong type of oil. Many products labeled as MCT oil are composed largely of lauric acid, or C12, which behaves more like a long-chain fat and does not produce ketones efficiently. As a result, people may be consuming the right quantity but not generating the metabolic response they expect. The distinction between C8, C10, and C12 is not a minor detail. It directly affects how quickly ketones are produced and how strongly the body shifts into fat metabolism. The second mistake is starting with too large a dose. Because MCTs are processed rapidly in the liver, introducing a high amount on the first day can overwhelm digestion and lead to discomfort such as cramping or loose stools. When this happens, people often assume the intervention is not suitable for them. In reality, the issue is usually one of dosing strategy. Gradual adaptation is essential. Another common error is ignoring timing. Consuming MCT oil alongside a carbohydrate-heavy meal significantly reduces its metabolic impact. Elevated insulin levels suppress fat oxidation and limit ketone production. When the goal is to shift metabolism toward fat utilization, the timing of intake, particularly in a fasted state, plays a critical role. Preparation is another overlooked factor. Simply stirring oil into coffee without properly emulsifying it leads to uneven absorption. Some sips contain concentrated fat while others contain very little, resulting in an inconsistent metabolic response. Blending creates a uniform mixture that the body can process more efficiently. Finally, unrealistic expectations often lead to early abandonment. The biological changes involved in metabolic adaptation take time. Expecting dramatic results within a few days can cause people to stop before the more meaningful adaptations begin to occur. Understanding the process allows for consistency, and consistency is what ultimately determines the outcome. Before finishing, it's important to add a note of caution, because even well-supported metabolic interventions are not appropriate in every situation. Medium-chain fats are processed primarily in the liver, so individuals with existing liver conditions should consult a physician before introducing them in significant amounts. For people with type 1 diabetes, or those using medications that directly affect blood glucose levels, changes in ketone production and insulin sensitivity can alter metabolic balance in ways that require careful monitoring. And for anyone taking medications that interact with fat metabolism or nutrient absorption, adjustments may be necessary to ensure safety. For most otherwise healthy individuals, however, the intervention we've discussed is not extreme. It does not require eliminating entire food groups, nor does it depend on rigid or unsustainable routines. What it does require is consistency and an understanding of how small daily actions influence larger biological systems over time. If you step back and look at the broader picture, aging is not driven by a single cause. It is the result of multiple systems gradually losing efficiency at the same time. Mitochondria produce less energy. Stem cells lose their ability to repair tissue. Metabolism becomes less flexible and increasingly dependent on glucose. These changes interact, reinforcing one another in a way that accelerates decline. What makes the research we've discussed interesting is not that it offers a miracle solution, but that it points to a common set of pathways underlying these systems. By influencing those pathways, through something as simple as elevating ketone levels at the right time, you may be able to shift the direction of that process, even if only gradually. The people who experience the most meaningful changes are not the ones who look for dramatic overnight results. They are the ones who apply small, evidence-informed adjustments consistently, allowing the body time to adapt. In many cases, the changes are subtle at first, but over weeks and months they begin to compound. Tomorrow morning, the only thing required to begin is a small adjustment to a routine you already have. Not a complete transformation, just a different signal sent to your metabolism at the start of the day. And sometimes that is where meaningful change begins. Not with something complicated, but with something simple done consistently enough for the biology to respond.